Anyway, but let's go to the real thing. So why this is important and why we all talk about that is that this protection, control, automating systems, they are going a little bit different ways, how the things are measured, and for the accurate measurement, also the accurate timing is needed. And it's not only the frequency synchronization, like in the past, PDAs, okay, when it's the time goes, tack, 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 that's important. We also need to know the time, meaning the time. I put it here, little bit maybe look like stupid, but yeah, okay, what is the time, what is the synchronization? So this is the most of what we know that, but it's something, time is time and date, so it's like your words, what time it's saying. And here now in the PTP, the seconds are nothing. We need to go to the milliseconds, microseconds, even to the nanoseconds, what is the accurate, and then we really talk the accurate timing. Synchronization, that's frequency, so how many megahertz, how many kilohertz. In the older technology, that was the most important thing. It's still important, and many times it goes hand to hand with this PTP. And okay. So where we can get this accurate timing. So now we talk about, mainly we talk about time and date and synchronization. So they're both on the same, but they are something that it's not possible. So the most common thing today is satellite navigation system. So normal people says GPS, and then they mean all this navigation system. But now we try to be a little bit more professional. So we should talk about GNSS, and then we know that there are different satellite types under that one. There will be a separate slide about that one, these differences and what they are, these four. And then some regional, which works in some areas of the world, but everything is like a satellite-based radio. So this is, maybe this is something in the history, someone maybe could know better, but then before these kind of nice systems, there was very simple, these kind of radio beacons sending the message, and that was only the frequency saying, tick, that's the time. But that could be combined also to the time and date. So saying, okay, now it's day this and that, clock is 12 o'clock, beep. And that's like how the radio signal works. At least I remember that in the Finnish radios, there was this kind of time signal every day, 12 o'clock, and you can check your time and set it exactly to the correct time. And local time sources, this is important. In this technical brochure, there are not that much information about this local time sources, and it's also the wording good to understand what does it mean. And now in this reference, we are talking about like the sources, and the atomic clock is one source. So also the GPS is giving you atomic time, but you don't have then this atomic clock yourself. This means that you buy quite expensive device with some cesium bulb or some other, and then you can get this timing. It could be that the owner of this atomic clock could be some like governmental institute. At least in the Finland, it's possible there are this kind of governmental research institute which has this kind of cesium clocks, and they can provide you time. You need to pay a little bit, but easy and less expensive to have own atomic clock source. For the other countries, I don't know. If someone knows, you can share your thoughts. Okay, something more about this GPS, or I should say GNSS, but GPS, like everybody says, because you have GPS everywhere in your mobile phone, in your sports watch, have that. But this is the original USA-based 24 satellites, and orbital is that, if that is something that matters. But what are the others? This is Russian. They have their own, of course. Galileo, this is quite new system, but European area should have also their own, and then the Chinese have their own. So 3 big ones. And in technical brochure, there are more details, like a data sheet type, where you can see what are the differences. But all of them can give you the proper timing, some small differences, but in higher level, all are good on that. And many clocking devices, they can reach, they can sync many of these, everything what is available, and that give you some security about the failures, and also unfortunately political issues that could be related for this kind of systems. So for some political reasons, they might like turn and adjust the accuracy, for example. That has been seen. But like now, the GPS, even there are some war in the Europe, it's still quite good, because okay, the both sides needs that, so cannot be turned off. This is like extra. This was not there in technical brochure. This is pretty new, maybe released after the brochure was done. But at least this is based what I know. I don't know everything. So, but at least in the Galileo, which is the European GNSS, there are now the plan, and it's not plan. It's all the specification is out. Is there any devices out? I don't really know. Maybe not much, or they are just like a trials. But anyway, they are like a authentication for the commercial services included the Galileo. For military wings, this kind of authentication is available. I think all the systems have for the military, but this is for the commercial authentication service, and this commercial means, for example, power utilities, railways, airports, this kind of, not like a normal guy like me, but for the utilities. And it will protect against the, not that much for the jammers, but if someone like tries to send the wrong code, wrong signal, it will authenticate this timing, and also positioning messages from secure server. It requires that somewhere is the server where it's verified and it sends the code, like some kind of authentication system. I don't know that much. Have anybody studied about that? Because it sounds quite interesting and might solve a couple of issues what has been seen with the GPS receivers. No. Okay, maybe not so many European people here sitting, so for others this is maybe not that interesting. Okay, the satellite, everybody knows where the satellites are, and it's coming over the radio. Satellite radio links down there to Earth. But there are something that can be done with the cables. So PPS, pulse per second. So that, as the name say, it's based on the cable, and in the cable are signal every second. So it's for the frequency synchronization, and also thinking about, okay, what's the topology where it can be used? It can be really used, let's say, inside the substation. You cannot send this PPS signal to not to the second building, I'd say inside the room for that. And this is, it's simple, and it has been there already long time. So many equipment have this kind of PPS. It's like this kind of very small coaxial connector. It's only frequency, but it goes many times together with the different, this is serial data format for the time and date. And it means that, okay, this ERIGP tells, okay, now it's 7th of September 2023, and clock is 4:55, and then the PPS signal says, okay, now it's the moment. So typically used for that. very commonly used, but maybe not recommended for the new designs. But for the old, it's okay. Works there as it is. Now, NTP, SNTP. So this is something that have to remember, that NTP is totally different than PTP. NTP is the normal time protocol. Well, the N is network time protocol, not normal time protocol, but it is something that like IT guys use. They use this to get the timing for their servers or something like that. It gives you what it says here, less than 1 milliseconds, tens milliseconds. So okay, it's good time, but I would call it that kind of worst watch accuracy for this. Depends where it's used. Can for the logging, for some events, it's fine. It will tell when something happened, but not for this kind of really like automation services, like any kind of protection related or synchrophasors. Not good for that. But very easy. Many devices support and typically no any extra cost to implement that one. But not for, let's say, to the real protection devices. For that is PTP. And what is nice for the PTP is that the accuracy is good enough for the most of the services. The media is Ethernet, which is the most common today, easy to find, no troubles for that. I would say that today it's much easier to create the Ethernet wiring than some PPS coaxials. I don't know even where to find the PPS sync cables. And this PTP, that includes the frequency and also time and date. So that's one. It's nice. Everything is coming there. And third, which is running over the Ethernet, is synchronous Ethernet, so-called Sync-E. That gives you a frequency only. For the frequency purposes, it's nice, easy to implement. Accuracy is good, but only frequency, no time and date. And last on this list is all good TDM-based signaling. So if there are SDAs or even interfaces, you will get the quite nice frequency synchronization that can be used for many purposes. And even as we saw there a couple of slides ago, so frequency is not only enough today, so you need to have also time and date information for the time stamping for the logs, everything like that. The frequency is still important. It could be a combination for that, like this, the protocols that give you just the time and date combined to any frequency synchronization gives quite nice results. Yes. So here we have that kind of comparison sheet. This is the information collected for the technical brochure. Everything should at least should be there. But I collected this to the one pager. It's a little bit easy to get the, let's say, so-called big picture. What is what? Because I know some people here are very experts for this and might feel this is boring. But some other are not that expert. So this kind of getting the big picture. What is what? So terminology, what they can use. Is it frequency? Is it time and date? Or is it both? What is the accuracy? So there are like a big differences there. Someone go to we talk about the nanoseconds, and some people talk about 10 milliseconds. It's like a huge difference for that. And also that's what is the application. No need to have any kind of overkilling solution if it don't need. If you just need to get the time for your server to get some log information, no need to spend money for expensive devices, time to do the complex configuration to get some nanosecond accuracy, what you doesn't need. Media, yeah, it's right, okay, if it's like a cable, or is it over the air, or fiber only, cable or fiber, this is also a little bit differences. And I see that also important, this read. So what is the topology? Because it's some times, or let's say quite often, it's just, okay, this is the protocol, it can do and this and that, but what is really the use case? Is it like suitable for the long distance wide area networking, or is it only for the local? So that's why added here, okay, local point to point. So it's like from the clocking devices for the user devices, or can it go over the wide area network? On the wide area network, we say, okay, it's from 2 to 2,000 kilometers. LAN is then, okay, 100 meters, like normally. What we have then after that, so PTP profiles. So PTP is, let's say, it's the hottest topic on that area today. And there are some reasons for that. One is, of course, that it provides the time and date and frequency. It can give you very good accuracy for that. And also it solves some troubles that has been seen with the satellite, or only satellite. So works nice also together with the GNS receivers. And also there are some special things that is like in the standard, and some equipment vendors are doing the devices based on that. And this is like the special profiles targeted to the power utilities. So this is where we start, so known as power profiles. So there are this IEEE C37.238, and then IEC has also the own number. And let's say, I don't know why there are like two camps for that, because these are, for my opinion, these are exactly the same, these two. This C37 has the older version, 2013 or 12, I don't remember, something like that. And that's then different. But this 2017, which is the latest one, is exactly the same as 618.50.9.3. If someone has better idea, this constellation, please raise your hand. Okay.
The C37.238 does support that extra TLV, whereas 9-3 doesn't define the time and accuracy TLV at all.
Extra TLV?
Its own proprietary C37.238 TLV.
Yes, TLV. And you say that in this IEC is not that TLV, time to live.
It's allowed to have that TLV, but it's not defined in 9-3. So it's C37.238 is an extension to 9-3.
Okay. So in the C37, the TLV is mandatory, but this IEC, it's optional. Okay. You can think to yourself, is this really needed to have two standards? But that's how it goes. So this is TLV, time in accuracy field, and this is really the information that is like requested by substation automation, or maybe protection device people, that they can get this inaccuracy information directly from the message. Okay, you can get it for the another ways. All these like switches and clocking devices can tell it to you, at least if you can use the calculator to calculate it yourself. It's not that these protection guys are stupid or lazy. It's that they want to keep their protection devices simple, so they can use the simple algorithm. They don't need to calculate that inside the box, because then if they can get this information from the message, and because in the topology point of view, these protection devices are like only the slaves always, so they can use simplified technology and make it easier to use, and maybe the cost can be then a little bit lower. What else? This is ITU-T. So this is T means telecom. So now I am on my own home base. So 6.5.1 is frequency synchronization, it runs on the layer 3, so it means that it has IP addresses for the messages, and this is the frequency only. And we have something PTP with phase and frequency, layer 2, and recommended telecom profile by technical brochure. That is written there in the brochure, and I didn't write that, but I fully agree that that's the right way to go. And a little bit same phase and frequency on layer 3. So this means, okay, now we have the IP addresses. What's the difference? Why the recommendation is there on this layer 2? Well, okay, it very easily goes back to the argumentation and debate between, okay, should it be layer 2 or layer 3, IP or TP MPLS, but it's not really same. Sure, there are something related to the routing. So if it's layer 3 routed, so it's that how these PTP packets are routed over the network. And in the PTP packets, it's very accurate that they like the path is constant. So that's why it's preferred to run it over the layer 2 to have the constant path for the packets for the better accuracy. So there are no need to the recalculation and readjustment so often to the clocks if we do it like that. And conversion of profiles. So don't be worried too much. Now we have 1, 2, 3, 4, 5 different profiles, and then there are older version of the C37. So quite many profiles, and which is good and what I should select and what is my recommendation. So don't worry about that too much. Many devices, especially if they are targeted to the power utilities, can convert these profiles, meaning that on the higher level, if they are like core network or something like that higher level, it can run on the telecom profile because it's the telecom network. But in the substation, you want to use some power profile, you want to enjoy, for example, this TLV information, run power profile on the substation and then do the conversion there somewhere like gateway type of node or the connection point between the substation and the wide area network. So it can convert the time and date, the frequency. That's not really converted. It's exactly the same. It's just what is there. The information on the overheads will be rewritten. Okay. Any comments about these profiles? Because this could be something that there are different camps or opinions. What is good and what is not. Okay. Then a little bit more about this PTP. So there are different so-called roles in PTP. Sorry, it's quite hot here. So the PTP devices, they can have different type of roles. So grandmaster, transparent, boundary clock. Also, it could be just a slave clock. Maybe not using that commonly. So normally grandmaster, this as the name say, it's the best master. Typically, it's your best clock on the accuracy point of view, or like your geographical topology point of view. That okay, I want in that city is my best clock. And transparent clock. Yeah, there will be later on a little bit more about that. Okay, what is really the transparent clock? What is really the boundary clock? And different kind of accuracy requirement. And now I'm referring that IEC standard. It defines 250 nanoseconds, 50 nanoseconds, 200 nanoseconds for different type of clock. You might be a little bit surprised. Okay. Why my grandmaster, even it should be the best one, has the worst accuracy requirement. So the reason is that really these transparent clocks and boundary clocks does not really create your timing. They just get it and maybe use by themselves and forwards. Transparent just forwards the timing. But the Grandmaster must somehow generate that PTP timing based on its own atomic clock or based on the GPS signal or based on something. So it creates, and that's why we cannot, or it does not make sense to set that requirements too high, because it's something that could be maybe impossible to do. But then when it's created, then it's wish that, okay, the other guys who are forwarding then don't mess with that too much. So that's why the number of this, or the accuracy of TCs and BCs is important, because you have many of these. And if we change, all of these guys might add their own inaccuracy on top of that. And then what is there on the end of the line? That's the interesting point. One step, two step. So there are also different flavors for these. So there are a lot of things that you can change and do the reconfiguration and adjustments. One is this: how many? What is the step thing? So is it like just one direction, or is it something that sends back this information what is collected? So maybe better accuracy, better results, but of course more data transmission, a little bit more to things to configure. So this flow of messages or not. Yes, so transparent clock. I added this page for the transparent clock, because this is something that if a little bit even interested about the PTP and think about, okay, do some wide area network planning or something related to telecommunications. Maybe B5 people does not care about that much, but BMC algorithm. What is that? So it's in the PTP devices is running that kind of algorithm, and it reads the PTP time and generates from the data labels the time. So the time and date and frequency, and the BMC is that it's like a protection. So the best master clock algorithm. So if, like typically in the network, it's some kind of ring or mesh, but more than one direction where I can get this PTP time. So the best master clock algorithm reads all of these and selects which is the best one. And okay, it's the protection. You will always get the best timing. You just need to set the priority cell. Okay, this is my master clock. Use that if it's available. Maybe you can set the priority 2 master clock station. Okay, I use that if the first one is not available. So the priority 1 is not available. And this what is nice here, the algorithm does it automatically. So it's very easy to set up. And it also blocks you like what if it's something like Ethernet network. No need to worry about these loops. So like a traffic storms or anything like that, algorithm takes care of that one. And also using that algorithm, you don't really care about the protection at all. You can run everything on the layer 2. So no need to worry the IP or what is happening on the routing. So you can have the flat layer 2 and use this BMC algorithm. But okay, not for the transparent clock. That's right, because as in the last page, it was the accuracy requirement for the transparent clock is higher. It should be better. So it has no time to do this algorithm. So it's just very fast forwards. Here in the boundary clock, we do that. So it's then about the network planning. So how to do it carefully, that you can maybe enjoy the benefits of the transparent clock somewhere, then use the intelligence of the boundary clock somewhere else, and then finally maybe use some power profile inside the substation. Something about that later on. Okay, don't resolve messages, so meaning that it does not read everything. It provides the transmission channels and can do the compensation, delay compensation, like everything. So on that sense, it gives the good accuracy, but it's like it's more like this kind of straight pipe than the actual PTP clocking device. Okay, you can read that from the brochure if you interested. It's getting too technical, too details. Okay, PTP device operating modes. I just put this because let's say the terminology is many times important that we talk about the same thing. So how these PTP devices now, any kind of device, what they can do and what is the operating mode. So okay, the frequency synchronization, it means that it will get the frequency somewhere, but not this time and date. Phase and frequency synchronization. This is wrong, sorry. It should be phase and time, because the phase is, for some reason, is kind of in this terminology, phase and frequency are mixed. I don't know why, but as you know, okay, the frequency and phase are the same things with a different scale. But anyway, this is the mode. Sorry about that. And holdover mode. That's also important to understand. And that's something that there are differences between the devices, how good they hold over frequency is. So in simple words, the holdover time means that you are getting the timing, whatever timing source it is. Another PTP Grandmaster satellite, and it's lost for any reason. So in the holdover mode, device has the memory. Okay, that was the frequency, that was the time. I used that. And the device can then run with the same frequency hours, maybe days, weeks. Then it's getting, is it possible or not? If you put more money on the table, you can run longer with this holdover time. But I think all the devices have at least some kind of holdover that you can manage at least few hours, maybe a couple of days with the same frequency, even you have lost your Grandmaster time. Finally, we will end up to the free run mode, which means that device running with its own oscillator. And of course, the day one when you power up, it goes to free run. Its internal oscillator, it's not that good, especially in the normal devices, because it's not targeted to run with that one. But depending the application, maybe it's not that bad situation, or it is bad situation, depending what are requirement. If there are some differential relays using the timestamping, sampled value messaging, it's critical. But if you just use some logs and maybe some TDM timing, free run, okay, no need to worry too much. It's not good, but you can fix it next day. If you are running sampled values, you need to run to fix it. PTP over wide area network. This is my favorite area here. And okay, the wide area network, telecommunication network, whatever is the naming. So now it's used the wide area network because it's another is the local area network LAN. Some might call that some kind of process bus or station bus, but process bus, station bus, they are Ethernet local area networks, so they are LANs. So that's why, okay, if it's inside station, it's the LAN. If it's like a wide area, it's the wide area network. And PTP over wide area network, that's like good that it is possible to do, to run the PTP over the wide area network, and it gives lots of options how to use it. So general requirements for good performance. Fiber connection between the substation. Yes, that's required, that you have your own private connection between the station. That if you buy the service from the operator, you might get good, or you might get bad, or you might get, okay, you do the acceptance test at link. Okay, all good, let's go that direction. But after 2 months, it's not that good anymore. That has happened. And properly designed packet switch network, IP MPLS, MPLS TP, both are okay, unless it's built well. So even these timing messages are not normally sent inside any tunnels. This kind of network that use the tunneling, pseudo-wires is good platform for that. And also, even they are not inside the pseudo-wires, they use the same physical interfaces. So the proper planning is important. These PTP packets, they are small, they don't need much bandwidth. So on that sense, no need to worry, but they are very tolerant for the time changes, so the jitter. So the latency could be quite long if it's always the same. So that what is for the good performance for the PTP is not really the latency itself, but the variation of latency. Combination of PTP and synchronous Ethernet. That's the one method how you can like mitigate the risks what is happening there on the packet network. So you get the frequency from the synchronous Ethernet, because that does not care how much data you are sending. Are you running 100% utilization or just a few packets? Sync-E does not care, because the Sync-E is not on the data plane. It's not any kind of packets. It's there on the frame. So on that sense, it's like SDH synchronization. So if you know how the SDH synchronization is built, you know how the synchronous Ethernet network is built. It has the same kind of SSM messages, even the names for the messages are the same, like in the SDH. So on that sense, it's easy. And it can be run combination with PTP then to provide the time and date. Combination of TC and BC clocks. Okay, this was a couple of pages before already. So what is the difference? So TC clock is this kind of fast forward, easy way. Boundary clock has more features, but it's more heavy. But in the bigger network, that might be the good way to use it. That because the long chain of these boundary clocks will end up, your time is not that good anymore in the endpoint. So in the bigger network, you need to think more like how to build the hierarchy. But that's the normal life for everybody who is designing wide area networks. This is just one more thing to taking care when doing the planning. Combination of telecom and power profiles. Okay, you can build all your network using the one power profile, but the scalability has some limits, and also it could be that the telecom guys want to run the telecom profiles, and the power station people wants to run the power profiles, and they are not ever get compromise what to use. So okay, then run on the telco network to run telecom profiles, and then on the substation run the power profiles, and sync them in some gateway devices. Boundary clock, more features. Transparent clock, better accuracy. Okay, this is in the one line what is there, the one page, so nothing new on that sense. What else? Okay, this is now, it's still PTP, but this is like a little bit different viewpoint, and that's like in this technical brochure. If you read it, my recommendation is check what is there on the table of the content, because there are so many different type of things. So just read what is your point of interest. And now we jumping a little bit, but that's how technical procedure jumps from the different things. We were on the wide area, now we go inside the substation. And inside the substations are a little bit different rules. Okay, maybe not rules, but the environment is different. And this is like, okay, how it's built inside the station. The scaling to the wide area network is just that I just enlarged the diagram because it's different topology, different stations, and all kind of things are changing. So this is like the inside the system, inside the substation. And it's like a topology where we have 2 master clocks and even 2 plus 2 satellite receivers, so 4 antennas. Why 4 antennas? It's maybe the weakest link of this GPS system is the antenna. So antenna, because it's outside, and under the weather conditions, it could be broken, or someone can do an sabotage, damage it very easily. Sending the fake commands to block, like this kind of jamming, is very easy for the satellite, and these antennas are not expensive, so it's easy to have many of these for the redundancy reason. So 2 clocks, master clock 1, master clock 2, they are like syncing also each other, and then we have slave clocks. These slaves, they could be then the boundary and or transparent clock. What is the best one? If it's like just the one station, not so many slave clocks, I would use these boundaries, but just me. And power profile most likely there inside the station, and then are these systems which are really the customers for the clock. These devices are using the clock, so they can be connected directly to the master clock. But if it's like a bigger station, you want to build a little bit like a hierarchy there inside the substation. So then through this slave clocks, and also it could be that these IEDs are simple devices. They maybe have just the one interface for the PTP. So then going through this slave clock devices will give the redundancy compared like here. So this guy is connected only for this one. If this fails, no clock. But this guy is going here to that one. So we have 4 options to do. So that's why it's good to have also some kind of hierarchy inside the substation. Yes?
If one of the GNSS fails, how does the master clock know that which one is correct? Like one of them goes off.
Well, if it's totally lost, then it's quite easy to detect that, okay, we are not receiving anything for that GNS. When it gets tricky is that someone can little bit adjust send a fake signal. And for that, these clock devices, they have, now we're going a little bit out of my expertise, but there are some algorithm that can, okay, compare if they are like a reference clock, another, they algorithm should detect, okay, this GPS is drifting, it's not normal, something is wrong. And for that kind of situation was that I talk about this secure authenticated Galileo. So it can then find this kind of situation that some kind of interference sends the wrong messages. Yeah.
That's also when we use the internal oscillator to be used as the source to compare against. So if you've got one source that's good from the GNSS and the oscillator is agreeing with that, you know that your single GNSS is flawed.
Yes, internal clock is also used for that. So it can detect that it started drifting. High-speed switching redundancy and parallel redundancy protocol inside the substation. So this is also inside the substation. So this is quite popular inside the substation to build some kind of redundancy, even having this kind of ring style, high-speed switching ring, or this parallel redundancy, so sending everything in two directions. Here are two pictures. There on the left-hand side, where this LAN A, LAN B. This is this PRP, which my master clock sends the timing message to both of these LAN A, LAN B, and the LAN works as a normal PRP LAN, and then the slave clock receives the same time for the both of the directions. So this is not same as I have boundary clocks and I can receive the timing for the two devices and then use this BMC algorithm to detect, okay, which one is the best. This is like a more primitive way to do it. So meaning that, okay, I send the same message to the two directions and I receive the same message to two directions in the normal day. And if one is lost, then I use another one. But this fits to this substation LAN, how I say, process push hierarchy, that it's built like that. So okay, let's use the same methods for the PTT. So it works here. Awesome. And then on the right hand side we have high speed switching redundancy. It's same principle, but the message is sent to the two directions all the time, and the receiver then decides what to use. The cabling is different. This is like a ring structure, so I would say much less cabling and better scalability of this ring structure, but some people prefer this redundancy architecture inside the substation. Both are, let's say, from the PTP point of view, both are okay. I don't see any differences. Differences are somewhere else related for this substation automation side. Okay, on the technical brochure, there was also a chapter about time synchronization monitoring, and that was a little bit like a discussion a few minutes ago. Okay, how to detect that there's something wrong on the clock, and that is one step to detect if the signal is lost or it is totally like wrong, and for that then the methods are pretty much there inside the hardware. So comparing for the reference sources, referring to the internal oscillators, and that works very well in one single substation. But if you want to see your network, all the stations, 100 stations, 200 stations, so that does not work there anymore. So monitoring system, so okay, everything should be monitored today. All kind of monitoring systems. So okay, time synchronization monitoring. So how to monitor that? So same principles for any other monitoring. So you can have centralized monitoring in your control center. Okay, it's looking everywhere. Or distribute. Okay, every substation have the monitoring server somewhere. Like say in every station, and they monitor and then they just report if something happened to the higher level. With scalability, and also it's like what kind of blueprint different and ways of operating different organizations have, but same kind of. And how to monitor this? When we look there inside the station, the monitoring is based really on the mainly on the frequency. And if the frequency says, okay, now something is wrong, do something, hey, I need help. But monitoring as really the frequency over this wide area, where it could be like 1,000 kilometers for end-to-end and many hundred stations, it does not work anymore, because how to measure there? If you are measure there, the data there in my far reach substations, the same measure, like the problems will be also my measurement data. So not possible to get any better information there than the devices. But we can collect the information from the devices there locally. So what we did there, that we compare the PTP time for our reference source and do the changes. Now we do the same. We use that information, but we don't do any switch, or we just collect and create the database over our network. So what we can do here, we can collect, okay, this is the good point for this inaccuracy. So it simplifies here a lot. If you this TLV information, you collect all your devices TLV information every 15 minutes, every day, every week, every year. So you will get quite good big data, what's happening to the network. And if something starts to twist there, some direction, you can get the already alarm there based on your data. How many steps? So normally that should not change, always the same. How many steps is from here to my master data? If it changed, something has happened. It's maybe not critical, but something happened, and maybe why. If it's happened very often, then maybe you should be a little bit worried. Okay, why is it changing? Offset to master clock. This is available also for the telco profiles. So get that information every 15 minutes. You can get the big data for that, and you can see, okay, is it steady or is it changing a lot? How much is much? Then that's the good question, where I don't have the answer now. Timing flow graphical presentation. So that's steps to clock master. That's like the number of that, how many steps I have for myself to the clock master. So then, okay, the graphical, so it's some kind of automatic flow or map. It tells that kind of flow diagram, how many steps and what are the steps from the one single station towards the master clock. And final thing on this page is communication between the monitor. So the monitor is like the device or measurement point there on the substation. And the server is somewhere in my control center. So how I get this information? So now there are two schools how to do it. Automation guys, they will of course use some Goose or MMS for that, because obviously that's the way how to collect the information. Telecom guys says, well, what are these? I want to use SNMP for like any devices. So both works well, depends about what is your software and how it works. Just one thing, that this automation approach, it works well from the IED level, but you cannot scale it for the whole network. You can, of course, use it for all your stations for that, but it does not go to all the levels of the hierarchy, because these telecom devices, switches, routers, MPLS devices, they don't create these Goose messages about what is happening with the timing. Why they should do that? Because the SNMP is invited. Okay, one more about this one. So just to get a little bit the idea about the hierarchy, what is what, where we can use with which layers. So in the control center level, okay, the GNS, receiver, grandmaster clock, atomic clock, so are there. Then on the wide area network, so okay, transparent clock, boundary clock. So the idea here is this is nothing connected. This is more like the bypassing devices. I use just the transparent here. I need to switch down. I use the boundary clock because I want to select which cards I connect here, this or this way. So I want to use the boundary here. This is not blocking, so it's not important. And then boundary clocks, maybe power profile here and end devices. I can have both here in the station, typically this GNS receiver, also in every station, PBS, okay, and this is used if needed. And that's pretty much it is in the simplified drawing different levels, different type of timing. So a little bit scalability thinking, okay, what is good here, what is good here, how to use this binary clocks, transparent clocks. Means planning, this looks easy, but if I have 200 stations, it's a little bit more thinking how to do it. Oh, all right. And a little bit about this application and requirements. So where are these clock needed? Now we are looking this from the perspective of the clock users. And now we are jumping for that substation automation and protection camp. And who is needing this automation? Everything that needs real-time data, real-time timing. So it means that you must always get the timing information, real-time process control, okay, protection relays, that's important, controllers, fault recorders, synchrophasers. So all kind of these devices requires the accurate time, mainly time and date, to get the samples, measurement values for just the correct time. And here we have that kind of table. This is also available there on the brochure, same information. So this is like a collected, what kind of synchronization accuracy is needed for the different services. And I would say this is quite important. Otherwise, it's easily happens kind of over specification. So require too much accuracy for the timing. So I want 1 nanoseconds accuracy everywhere. Okay, you can have it, but it's not easy to do, and it costs a lot. So that's why it's like having, okay, well, how much is much, how much timing I need. So if I just do some metering, so or computer system monitoring, so NTP is fine for that. But if we want to use some synchrophasers, 1 microseconds, okay, then we start to talk about PTP with good design. Not that much anymore. So conclusion and recommendations. So what we have a little bit, this could be a little bit repeating, because on this slide set was collected mainly these conclusions, and full information is there on the technical brochure. Satellites, they are good. Multi-constellation means that, okay, we can check, we can check the US satellites, Chinese, Russia, European, everything with the 1 devices, and they can know how to change and compare these. This like help a lot about the satellites. Of course, if someone comes close and brings the jammer close to your satellite receiver, these won't help. I have heard many examples about these jammers, how easily they are. So someone going in the 1 power station, there was a situation that, okay, the GPS clock were lost every day about 12 o'clock in the daytime, but only on the weekdays, about 30 minutes, what's happening there. And people were looking there, all good, no problems. And then after time, they did, okay, let's go there on the substation then at 12 o'clock and see what's happening. And what did happen there was, close to the substation was a house. There were big truck, big drive there to the yard, and then the clock starts working. GPS were lost. What happened? Why it's happened now? Then after 25 minutes, the truck starts and went away, and the clock came back. Okay, it ended up that the truck driver lives there next to the substation. He was not allowed to drive to home for the lunch. during the working time. So he did buy from the AliExpress GPS jammer, turn it on, drive to home to have the lunch, and when he eating, drive back. So it's easy, and that's why running only for the GPS, even like any kind of multi-system, is not very reliable. Protection system application may rely on the sync. Yes, at least the modern things do, and then it's getting the critical. So if the timing is lost, it's not affecting only to the logs or some measurement data. It will affect also to operations. So the protection delays, it depends the configuration. Most likely they go some kind of fault mode in that moment, that the differential protection just don't work because it does not know the timing, or it has some kind of backup to do it. Samplet value 1 microsecond. It's quite good, or requirement. Let's say heavy requirement, but today it's doable. Goose, okay, it says 1 milliseconds. Not that high accuracy requirement for the goose. For line differential, so this is many times in the discussions, and for the reason because it's important and it's quite tricky sometimes. And ping pong algorithm, it means that these differential protection devices that calculates with this ping pong what is the delay between the station. And the delay between the station must be used as an offset when they send the measurement information. So the data timestamps for the measurement data are adjusted by the results of the ping pong. Someone most likely knows better how it works in practice. But anyway, it can find what is the delay between the stations. But that is based that your both directions are on the same time. And with the timing, if you have the PTP timing, you don't need to use this ping pong to adjust. You can use the PTP timing to do the sampling. Of course, another way how to avoid the problems for this ping pong is that you use just some wide area networks that is really like zero asymmetry. Maybe best way is use the both. Use some one communication that is really like zero asymmetry type pseudo wires, and then use this GPS or PTP timing as a second option to make it working well. Because if let's say this ping pong fails, if it's totally fail, I believe every device can detect that one of the differential device, at least what I have seen in the testing. So if we got the fiber, okay, everybody knows something is wrong. But if the timing drifts a little bit for the wrong direction, then it does not detect that it's going wrong. And then it's really possibility that there's a false tripping happening. So that's why it's important. PMU, so synchrophasors, this is also this 1 micro class. GNS, okay, should have a backup source, and I think that's quite common to have the combination of the PTP and satellite receivers. One, if you have the fibers there, okay, run the PTP and use that together with the satellite receivers. And then there are kind of redundancy, different type of technologies used at the same. PTP profiles record, i.e. this one, yes, that's, sorry. This. So different profiles, different purposes, but no need to put everything in the one basket. You can have the combination of the different profiles, different type of clocks in the one network. There's one good point here. Okay, if you select some devices, it might sound non-relevant, this leap second thing. Okay, leap second happens some like adding the 1 second there, or was it extracting the 1 second of the time and date? What's the matter? But if we are now talking the microseconds, it's important. So if this is wrong in leap year, your system will collapse if this is not correct, because the 1 second is like million kilometers when we talk about the microsecond accuracies. Okay, holdover is something that have to keep in mind. You can get better holdover many times just upgrading the hardware, but it has a cost. Is it cost worth of paying? Is something that need to think about. And also it will, okay, if you have the redundant clock sources, maybe the holdover is not that important anymore, because it's very unlikely that you need to run with the holdover a long time. Redundancy, yes, that's like, because it's important and critical system, we need some kind of redundancy. Master clock with high quality internal oscillators, yes. Satellite redundancy, control center optical fiber, PTP, applied ring mesh networks, yes. Network topology, PDP. So it's like the combination of all of these. So one is that, okay, should be more than just the one, let's say that the priority one clock source. If you use the satellites, then maybe somewhere, at least some like high quality oscillator clock, atomic clock, or something like that. Not only one. And GPS, okay, different type of signals. That's quite easy today. Backup fiber optics, yes, use the fibers also for the timing. Most of you have it. Boundary clocks, so the planning of the timing, especially if you go over the wide area network. So to the topology planning, different type, okay, transparent boundary clocks, little bit with the hierarchy. So little bit thinking like any network device, any network design. And inside the station also this, if there are already this PRP or HSR, you can use this for the redundancy inside the station. So different, I would say that my like personal message is that different hierarchies can be built different methods. So not like one size fits for all, especially if we're going there inside the substation over the wide area. So different topologies, different practices, but it requires, I would say that this like in this technical brochure, P5, D2. So even there are special areas of the interests, different like responsibilities. This is the area where the protection people, substation people, and telecommunication people should be cooperating. It's just that, okay, this is the socket, connect that, do whatever you want. Won't be good end result then. This is the last. Okay, requirements for communication and switch. Okay, of course they should have the support for these protocols. What is used, minimum application specific path delay. Could be differences between the devices. You can maybe get some information from the manufacturer, or then you do some testing. If it's something that let's say targeted for that kind of use, no, maybe you need to worry about that one. This is maybe more the worry of the IT people. And to guarantee the operation, okay, FAT, system level tests, all kind of testing. Yes, makes sense. This is new for quite many people. Even this PTP has been there long time, but not necessarily on this kind of application. So doing the testing to see that everything is working. And okay, the FAT that tells, okay, the device is good. It's more like on that phase when you want to evaluate, okay, is this good gear or not? But then how to do in the real environment, like acceptance of the services. So the configuration is made, everything is there on the station. So yes, it makes sense to run some testing there. Maybe you need for some new test devices supporting these PTP functionalities. Makes sense to test after the commissioning that everything is working fine. But also important is that what's happening then when it's into use, because okay, the total bandwidth could affect the PTP performance. That's something that you maybe don't see when you do the commissioning because things are changing. So then this monitoring, how to monitor your PTP time when it's running is also the important functionality that you can see what is happening. And distance between the stations could have the effect because it's already hundreds of kilometers. That's like microseconds going very quickly. So it's different if you have 2 boxes in your office and you have 2 boxes and there's 200 kilometers between them. So everything, many kind of things to be worried. But on the other hand, it's not that difficult if you don't make it too difficult. Okay. Maybe I did use all the time what is promised for me. And it seems that most of people are still awake.
Does the actual distance or is it more the number of hops?
The number of the hops is more important. Sure, they are like the light of speed is something, but it's always the same. So in that sense, it does not matter that much. It's more like really the number of the hops, because every hop will affect, because they are like the equipment, and every equipment, even good, how good they are, they will have some inaccuracy. And the number of the hops, because it's calculated, like there were somewhere these inaccuracy requirements. So it's per box. So every box adds that amount. And also this bandwidth, that will affect what is the performance. Even you have all these like parameters set well, they are still some single port where everybody wants to go. So even the BTP packet has the VIP queue, can go first, but if someone is just there on the door, also the VIP needs to wait. Not long time, but little.
Can I just add to that? You've got dispersion in the fibre, but there are methods to factor that in to compensate for that. And also, if you're implementing ITU-T G8275.1 and you're using high performance boundary clocks, you can distribute, which have time error less than 5 nanoseconds per hop. You can achieve high levels of high accurate distribution over the comms network.
And then based on your shirt, you should know something about that.
I wonder if you might comment on the partial on-path support for PTP, where an intermediate node doesn't support either SYNC or P2P in transfer.
Then you are in troubles, I would say.
How much trouble?
It's very hard to say how much. In the best case, not much. Like if you have some switch without PTP support and the total load is very low, okay, it goes there quite nicely. But if there are load the compensation is kind of lost. So maybe you have some practical comments.
There is APTS, which is another telecom protocol. I can't remember the version, might be IQGA 275.3 or something like that, which you can characterize the error through a path. We've got a timing source that has GNSS and when the path changes, it notes that the path that's been taken, and it can compensate a lot of the error of those non-PTP aware devices. If there's a will, there's a way.
Yes.
Regarding the monitoring approach, have any universal approach to monitor the devices, PTP devices on the WAN side and LAN side at the same time? Any practical approach to monitoring the PTP parameters?
So the PTP devices, so monitoring this, so you can collect the information for these devices, but if you want to you want to like a forecast, okay, what's happening? So am I losing the timing or not in the near future? So if you collect the information every 15 minutes, you should have the data that if its clock starts drifting, you should maybe see there on the data that something is happening. Then it's up to you. Can you set that kind of alarm there that, okay, it's not lost, but it's going to the wrong direction?
Sure. But my question is that there are many different suppliers of PTP devices.
Yes.
So how to monitor the different vendors' devices parameters to calculate?
There are standard PTP MIB. You know something, I saw your face.
Yeah, if it's supported, there are some parameters that you can monitor within various MIB files, but yeah, it depends on whether it's supported. It is optional as to whether you support the MIB or not for particularly things like C37.238, I think it is, off the top of my head.
Yeah, there are basic information there in this PTP MIB that can be used, or otherwise it requires that kind of when the vendor or the equipment specific script. So I can say that in your monitoring system, someone has to tell, okay, in this type of device, ask that parameter.
Hello, thanks. My name's Gareth Taylor. I'm from Brunel University, London, the UK. I'm also a member of the Strategic Advisory Group, SAG, for D2. So thanks for an excellent presentation. One thing I'd just like to ask is, you did mention, I thought you mentioned the concept of time as a service, or maybe a utility approach to providing timing or time. And I'd just be interested to follow up on that. I know in the a couple of countries now they are looking at that. I know NPL Labs looking at that in the UK, and also NIST in the US. I just wondered if you've got any thoughts on that, or what that might mean in the future and this kind of work. Thanks.
What I know, yes, I didn't mention from that word, but I think your wording is just correct. Time as a service. So what I know in Finland is that this governmental research institute, they provide this timing as a service. So they have a cesium clock, and they create from the cesium clock PTP timing, and then you can, if you pay some monthly fee, I don't know what it is, you will get 10-day PTP timing there, and that's like one option. Of course, then where is your access point where you connect to your network, that timing, that's also a little bit critical, that you don't mess up with this timing when you get it.
I was going to add, we've seen a few customers try to roll something like that out, but a centralized thing because they don't hold it themselves. And so there's a control thing in some cases where they don't trust this global, this time scale from a government organization, and that they much rather own and operate it themselves so they can control how it's run, how it's managed, how it's monitored.
Yeah, that's right. But and maybe also if using this kind of time as a service, it should not be like a one and only source for that. Yes.
I was just going to pretty much say that. So the other issue here is if you're using time synchronization solely from the communications network, if you have a major environmental event or something like an earthquake, it is possible for those communications networks to get severed and we lose that timing. So it is advisable to also have other signals of opportunity, GNSS, communications over, communications network, and whatever else you can get hands on to validate, and it also, as you've also brought up in this presentation, mitigates against spoofing and jamming.
Yes, correct. They're back there. You have been waiting for why?
I'd suggest though that if communications has gone down, you probably don't need that global synchronization anyway, because you need that global communications to be able to rely on the global numbers anyway. But I think one thing that I didn't see in the paper was the performance of different devices and the network time synchronization system as a whole during recovery of global time. We focused a lot on holdover times and maintaining stability as much as we can. But during the recovery phase, like if we've lost that global time and it comes back, that performance isn't often managed. Do you have any best practices on that sort of recovery?
Yeah, there were nothing about that in the brochure. But it's right. It's important, and there are differences between the devices. So it could be like a different vendor are doing it different way. So what is the recovery time that can change, and maybe the vendor can provide some data for that, or then it's just a part of this acceptance testing that, okay, how it's really on. It's like a one test case for that. But please.
Okay. I won't give too much more information, but just create awareness that there is a emerging standard, IEEE P1952 working group, which is the resilient position, navigation, timing, and end user equipment. End user being defined as something that ingests timing and then outputs that. And that relates back to the power industry, and we're developing use cases for that, sample values, line current diff, you name it, it's there. So you'll see something coming out of that in the next 1 to 2 years. And the idea behind that is it'll be testable. They'll put through various types of PNT disruption. And there'll be some test methods and things like the IEEE ICAP program will develop some way to test product to see what its resilience levels are, allowing end users, power utilities to decide based on what level of resilience they need for the applications and their budget as to what they go forward with.
Yeah.
Thank you. Herbert Klima from Austria. Thank you very much for this really interesting presentation. A question to the master clock, please. There are several time sources for the master clock, including an internal clock as well. Is they are calculated from the master clock one average time, or can it recognize the best one?
You mean there in the PTP? So how the master clock is recognized? That's so-called PMC algorithm that detects what is the master clock. So one thing is that they are the priority for the PTP clocks. So the best priority should be selected always the first, and then the second one. So they could be. It's not just the one priority. There could be several priority. It was 128 even the levels there. So you can build very complex hierarchy map there. So what order you want to do it, but maybe just having 1, 2, 3 like a higher level clocks, and then let the algorithm decide. So it will find out what's the best one, and also what I like, it just take care about this link protection. So if the link is failed, it will move automatically to another one, and you don't need to worry about any kind of loops or anything there. It does the work for you.
Thank you.
You did not mention that one use case I found was that once all of your clocks and all of your backup clocks fail, you need to have your workstation still synchronized with the server, because there's at least one SCADA system from a major vendor in the world that if the workstation clock is behind the server clock, then it will not display the events and the alarms. So you must have a final backup for your workstations that it actually synchronizes with the server, and you disregard the fact what is the clock in the real world.
Yeah, like a final backup for everything. And I don't know, maybe if you have a clock device there on the station, and the GPS is lost, and maybe the fibers are cut, everything is down, it still have the internal oscillator. And if it's clock device, it's better than average internal oscillator. So that's maybe could be your final backup.
Point is test.
Yes, how it works, yeah.
Yeah, I'm Lily from NR Electric China. Thank you for your excellent presentation. My question is about, do you mean that we can get rid of the ping pong algorithm when we use the PTP for wide area communication?
My opinion is yes, but maybe better ask someone who knows what's happening there inside these differential protection devices. But the ping pong algorithm is that the deep time between the station, that is used for that. And if the timing is get from the GPS, it will get, or any PTP, whatever is the timing. No need to use that ping pong to get the timing.
I know.
And on the same way, no need to worry about the asymmetry anymore. I know that I have seen some differential delays which is possible to change from the ping pong algorithm to PTP or GPS. How well it works, I cannot say. We didn't test that on that.
Yeah,
time.
exactly. But I don't know how many protection guys here. You know that the many protection guys are worried about the external time reference or time clock.
Yes.
So do you have any solution to simulate the definite time delay or in the communication tunnel so that we can use the legacy protection device to adopt this your solution, the time synchronization solution? Yeah.
So you mean that like
yeah, you mean that you can simulate the E1, or we can actually simulate the E1 channel for protection. Use your packet-based wide area communication.
Yeah, the packet-based communication can be used for that, and
so we the protection can use this simulated E1 for protection.
Emulated.
Yeah, or in this solution we can also use the ping pong algorithm.
Yeah, that's possible to use the emulated E1 over the packet switch network, and in that case, the timing is needed for the circuit emulation.
I know. Also, Alan, thank you.
Right.
For example, you got 20 hops to cover.
Yes.
And then you, with your PTP, you only can do up to 12 hops, for example.
Yes.
Will you put your master clock? Do you put it on the first one and 12th one, or do you go first and the 24th? Like, do you come this way, or how do you put the master clock on the network?
I don't know. Maybe if I have to do, I would put there something there in the first and then the middle, but that's not. I'm not doing the network design in my work, so maybe someone can know it better. But
Yeah, you can do bi-directional PTP with certain product on the market, and like I mentioned before, it all depends on the maximum time error that the boundary clocks in between add to it. So you can get some product out there that is has very tight, less than a few nanoseconds, which allows quite a substantial number of hops before you start encroaching on the danger area where you can no longer meet as far as a protocol converter from PDP telecom to your power utility profile. We start to get into that 250 nanosecond range, which is what you need for the T5 IEC 61850-5 T5 timing requirements, which is 1 microsecond.
With a PRP connected PTP client,
yes,
normally the messages that are not the PTP messages are have the same payload, and you can discard one of them. But the PTP messages will be different because they're coming from different sources, different delays, different follow-up messages. Whatever.
yes.
So what's a good strategy to choose, or how to process those two different messages?
Well, if we connect this PTP, so that timing messages with this PRP, so the another redundancy protocol. So okay, the redundancy protocol doesn't care what is there inside. So it like acts like any data. I don't know. Can I roll back to that? This. So it will send to two direction, and it is a little bit that kind of two cakes top of each other. So this PTP having their own algorithm, but then the PRP is on top of that, and who decides is the PRP in that case. And why to do it like that? I would say the only reason why to do like that is that the substation is already designed like that, and just need to live with this specification what is already made.
If we're talking about the 62859-3 profile though, that's covered by 62439 part 3, I think. And in that case, the slave clock actually does the best muster clock algorithm and looks at both of those two incoming signals separately, and that's a requirement at that standard. So in the end, the tiebreaker will be the port number that is coming in on if they've got the same accuracy and all the other parameters.
Thank you for your good presentation. I'm Katsuhito Sawada from Japan. And basically, I concerned using GPS for electric power facilities. GPS have the security risk and reliability risk for electric power facilities. In my memory, Singlet 22, the paper from China described getting time information from 5G. So you are also working with a 5G member. Yeah. How do you think getting the time information from 5G?
Well, this 5G was not included to that technical brochure. Maybe one reason is that when the scope of the work was made, the 5G was not that it was still on the development, so not really information available. So it's not on the technical brochure. So that's okay. That's just now my personal view for that in the 5G, there are good timing. I don't know, cannot say, is it like a microsecond or tens of microseconds for this there available. So that might be a good option, but have to remember that the 5G is, and also in the future will be limited on only for this kind of, let's say, the city areas. It will never be there on the rural areas. It's just the coverage for that. But for the city areas, that might be in the future one option to build the redundancy for the timing. So using the 5G as a one timing option. Do you have anybody studied for that more, that how to get the accurate timing over the 5G networks? You have.
Not really. One of my colleagues in the US are experts in that, so I'm not going to put up my hand for that. But typically they need 1.5 microseconds off the top of my head at the nodes. So reality is that with the current technology, you're not going to meet IEC 61850-5 T5 performance with that sort of accuracy at this stage. But you know, technology will evolve, and no doubt we'll do a lot better moving forward. I'll leave it at that.
Thank you.
Thank you for your interesting presentation. My name is Mitaku from Japan. So I have one simple question. Last slide shows we have to consider the bandwidth how to use the PTP performance. So how many bandwidths do you need using the PTP?
Not much, I would say. On the brochure there was no that kind of data. At least I remember there was not. And on my own head, I cannot say what's the actual bandwidth for this needed. But I would say that it's not too much, and the bandwidth it's not really the issue there. What you need for the PTP, the bandwidth is coming that what the other services will consume the bandwidth, because if it's like a fully allocated device, so even the class of service and all the priorities are built well, there still will be a little bit more queuing for the PTP packets, even they're there in the WIP line. So on that sense, need to think about, okay, never let go over 80% or what is like the planning. But if you're running 100% on your link, the PTP performance won't be perfect then anymore. It is affecting on that way. But I would say if 80 below that, you will get the high priority. These VIP guys always going fast enough.
Oh, all right. We need to high priority. The PTP packet set to the high priority.
Yes, that's good.
That's right.
Yeah.
Okay, thank you so much.
Hello. Regarding the previous question, I want to you to discuss more about the in terms of the network provider, what do you have to give the time synchronization to meet their requirements, like the quality of service of the packet, or the path delay and the protection path of this kind of time synchronization. So what would you suggest? Thank you very much.
Good point. Maybe one important parameter there is that variation of delay. So that's important for the good PTP, that okay, there could be some delay latency on the link, but if it's always the same, no worries, it can calculate it out what it is. But if the delay is changing, then the devices need always to try to adjust for the new situation, and that will definitely affect to the performance. So it's like a time delay variance is more important than the delay itself. But running that over the leased line, so if you buy the service from the operator, maybe a little bit risky business to do it, but I cannot say anything else about that. Okay, good. Thank you. There were a lot of discussion, and that's good to get another viewpoint, and also you can share your expertise about this area, and even this technical brochure had lot of people involving from different backgrounds. It does not cover everything, as we noticed, and maybe based on these discussions can be started even the new working group to continue this to answer these questions what was open here. So a lot of things about the PTP, but maybe everybody understands that timing is important in the modern systems, and for example PTP is quite nice path to timing delivery. Even it should not be maybe the only one, but combination of different timing methods is maybe the message for this day. So thank you everybody that you